There are many methods that can be used to detect performance drift. We have already learned about novelty detection and outlier detection algorithms, so we will demonstrate drift detection using these methods. We will also include a test that uses a distance metric to help detect distributional changes. As a reminder, outlier detection is distinguished from novelty detection by whether or not outliers are assumed to be present in the training data. If you think about it a little, these methods have uses beyond drift. For example, maybe you have, say, a deployed classification model and you would like to monitor for aberrant predictions. You could also monitor the input data for a given model by asking if it is similar to historical data. If we define performance as any appreciable change in model performance between a null and test dataset, then we need to talk about the null dataset. The null dataset can be defined in many ways. It could be all historical data, it could be all of the previous year's data, or it could be just the data from the most recent training batch. The null distribution in this case is going to depend on the business opportunity. One form of performance drift is known as concept drift, and this is where the statistical distribution of the target variable changes over time. We will use the iris dataset to generate batches of data in a way that simulates a form of sampling bias, which will cause concept drift. This is not the only possible form of sampling bias to be aware of, as there could be underrepresented groups within a dataset that are not directly related to the target variable. For this example, though, we will use the class proportions in the target variable to demonstrate drifting model performance. Let's have a look quickly at the functions that we will use for this demonstration. The train model function is very similar to the other train functions that we have seen up until this point. We are not logging any of the data associated with the training, but in a normal production scenario, you would keep track of runtime, model version, and a summary of the classification report at a very minimum. The predict function we are using is a minimal implementation in terms of how hardened it is to different inputs. For example, we could add checks for the correct number and format of individual features, but this is enough to showcase the general process of detecting drift. We are logging the predictions, the probabilities associated with those predictions, the query itself, and the runtime. This is the function to write to a log file. This function could be bundled with other helper functions as a class or a Python module, but for a minimum, we show it just simply as a function. Given the row entries, the file is opened using the append mode, and they are written along with a unique ID, a timestamp, and a model version. We have hard-coded the model version at the top of this notebook to keep the example concise, but generally it would reside inside the model.py file or somewhere similar. This slide shows the functions in use. First, we load the iris data, limiting it to only the first two features. Because with all of the features, the classification problem becomes too easy and makes the demonstration unrealistic. We show how to train the model and run a query, all functions that you are already familiar with. Here we have a function to simulate new samples using the bootstrap, which, as a reminder, is sampling with replacement. We see the original data has balanced classes, as shown with the counter dictionary. We then run the simulate samples function to see how the data change. Here we simulate a bunch of data where the percentage of class 3 is taking up more and more of the overall feature space. The percentage ranges from 33% up until 92%. Recall that the original F1 score a few slides back was 0.78, so that means that our model performance stayed roughly the same, with maybe even a small increase in performance. This implies that if we were monitoring based on F1 score alone, we would potentially miss out on the fact that we have very unbalanced classes. SVMs, if you recall, can do quite well with class imbalance. We were only able to calculate the F1 scores here because we know the true predictions. This would be analogous to waiting until the query data was labeled and then coming back and checking whether or not the model performance is drifting. There was a major shift in the distributional nature of our data. Given such an extreme change in our data, we would want to know about it even if it was not readily apparent by looking at the logged evaluation metrics. So here we are testing for outliers using the elliptic envelope, a variance-based method. It is important to note that with this method, we are looking for outliers, not distributional changes, which can be related, but they do not necessarily coincide. To specifically look for distributional changes, we use the Wasserstein metric. We run both of these checks on the features and on the targets. In a typical deployment scenario, we would not have access to the true labels, so we would not be able to calculate the Wasserstein distance between known and predicted targets, shown in the third column. We would, however, be able to check for outliers on those targets, the last column. We see that the distance metrics do a good job detecting the drift in the target distribution. The test that is the most important is, of course, the one that is at the level of x. the second column, because these data would be readily available. This example has an additional benefit in that it demonstrates a way to guide the setting of thresholds for throwing flags. We used bootstrap data, so in reality any outlier that was detected is really part of the normal distributional variance. This implies that a strict threshold could be put at say 5% for outliers, and a more permissive threshold would be put closer to 10%. One final note to keep in mind is that when dealing with data that have many features, it is a reasonable practice to reduce the dimensionality of the feature space with PCA before calculating distance and detecting outliers.